All right, everybody. Hello, welcome back to Colloquium for this week. This week, we're honored to have a very distinguished speaker from the APS department, Professor David Malaspina. Good job, I like the energy. David was an undergraduate at Purdue University in 2000, and then he went on to graduate school here at the University of Colorado in our friend and neighbor department, physics, and graduated with a PhD from the physics department. He was a research scientist at LASP for several years and then joined the faculty here in the APS department, I think in spring of 2020. It's a great time to join the department. Good job. It was all downhill from there. David is an experimental space plasma physicist. He thinks about physics in the solar wind. He thinks about Earth's ionosphere. He thinks about the plasma environment near the surface of the moon. He thinks about how spacecraft charge up when they are exposed to sunlight or other particles, changing the charge state of the spacecraft. He thinks about lots of things that I'm probably forgetting, and he also thinks about the sun, which will be the topic of the colloquium today, his efforts with Parker Solar Probe. So without further ado, I'll turn it over to David.
Okay, thank you, Dave. Much appreciated. Welcome, everybody. So today I'm going to talk a bit about Parker Solar Probe, some of the things that we've accomplished with the mission so far, and in particular, the projects that folks from CU have focused on. And then that's the there part of this. And then the back again is what has come out of the work that we've done with the Solar Probe mission. It has led to a whole range of CubeSat and rocket and other projects that are exploring the near-Earth environment and the lunar environment. But it's all kind of started with this Solar Probe project. Okay, so very recently, in fact, just before Christmas last year, Solar Probe got the closest to the sun that it will ever get. It reached 8.8 solar radii from the solar surface. To give you context, Earth is at 215 solar radii, so we got very close. These are the ones I use for public talks. We got to the 4-yard line. If we're thinking of it as a football field, if you're thinking of it as a 14er, because we've all hiked those, you're 600 feet from the top. You're basically there. It has been a long road to get there. This goes all the way back even to the 1950s. So in 1958, there was a congressional committee that recommended a solar probe mission be formed or formulated. And that was almost coincident with the founding of NASA. So since the beginning of what we consider space exploration in the United States, there have been a push for a solar probe. The first direct measurements of the solar wind were in 1962, Marcia Neugebauer, so list shown up there. And then, I don't have a, damn it. Okay, I'll do this. Thereafter, every 10 years or so, kind of as an annual exercise, NASA sat down and said, let's do a concept study for what Solar Probe could look like. All right, so they come up with a study, nothing would happen. They come up with a study, nothing would happen, and repeat for 40-odd years. Around 2003-ish, it got pushed through to the point where it said as soon as possible was the congressional recommendation, and then it was immediately canceled. Yeah, you see how these things go. But then 2 years later, it came back again, and there was this push, and it got kind of into the decadal process, or what was the pre-decadal process at that time, and was called the highest priority for new resources. At this point, we get pushed into it got reformulated as Solar Probe Plus, right? Because we all know plus means better. It actually is better for a lot of reasons, but the marketing was a little obnoxious. Anyway, after that, there was proposals for the instruments went in about 2009. Selections were made in about 2010. And the instruments and spacecraft were finished building in about 2017, launched in 2018. The first perihelion pass was immediately following that launch. And then the closest approach happened just at Christmas time last year. And the program is still going. I like to show this picture. The office that I sit in on East Campus, Jack Gosling used to sit there. And if any of you know, Jack Gosling is a very famous solar wind researcher. And he left behind a lot of these solar probe reports. So all of these different concept study reports are sitting there in hard copy in that room. And I kind of inherited them, which is really fun. OK, so why do we work so hard? Why spend 60-odd years trying to get to the sun? For a lot of reasons. How do I show this video? Good. This is a video. Nope. There, go ahead. There we go. I'm going to play this video in the background. This is courtesy of Zach Berta-Thompson, our very own. What you're looking at here are the aurora from lions. Good job with the video. But the reason that people have pushed so hard to understand how the sun works, there are many reasons. One of them is the sun-Earth interaction, right? What happens at the sun can affect what happens on Earth. And it's more than just gravity and photons. Those are interactions we know pretty well and are pretty stable with respect to time. But solar wind particles and magnetic fields that come from the sun change what happens in the near-Earth environment. It changes our radiation belts, our magnetic field, our ionosphere. It can even get down into the atmosphere. So what this does is it creates this sort of daily, monthly variability of the magnetosphere, of our ionosphere. It can even get down, if you're thinking about ground-induced currents, into the surface a bit. So we call this space weather, right? Weather with the idea that it happens on human timescales, space with the idea that it happens due to a cause in space. And here's some examples of space weather phenomena. So as the solar magnetic fields and particle environment changes, that impacts what happens on Earth in terms of sort of astronauts and spacecraft. You might think of radiation damage. You may have noticed that polar airline routes are rerouted during major solar storms to try to avoid the electrons that precipitate down into the atmosphere. You can see the aurora, which we just showed on the other slide. That was a view from Lions. So these are things we can see every day. You can also get what's known as ground-induced currents, meaning when currents flow in the ionosphere, you get kind of mirror currents under the ground or in long conductors that humans like to build, like oil pipelines and power grids. So these are things that affect our daily lives. This is the other reason why people are very excited to go explore the sun. There is exactly one star we can do this with, and it's the sun. Right? So if we want to understand how all the other stars work, we can, of course, observe their photons, but at some point you're limited by just being able to see the photons. You really want to get up close and measure the magnetic fields in the plasma in as much detail as you can, and that we can do with our star. Other things we can learn about stars, we know that stellar winds, for example, around other stars drive angular momentum loss. We know to some extent they can drive mass loss, and we know they can affect atmospheric retention around exoplanets. So how that star behaves can affect the whole stellar system. The fundamental challenge here, how do we measure the sun? We measure it with remote sensing, right? We measure the photons that come from the sun. We've done this for centuries with telescopes. We can also measure things in situ, meaning measuring in position or in place. Right? So at the point of the spacecraft, the environment around it. Not a messenger from a distant source, but literally the environment that the spacecraft is immersed in. Those are in situ measurements, and that's what Solar Probe is mostly doing. The issue here is that what we've been trying to understand is what happens at the base. Right? We're trying to understand where the solar wind comes from, how the solar wind magnetic fields end up propagating through the solar system. But we've been doing it by looking, so we're basically trying to understand the process by which the wick is burning and releasing material. But we're trying to do that either by measuring the photons from the flame or by trying to measure the smoke in situ from a long way off. That makes it really difficult. What we want to do is get as close as we possibly can to that source region to understand what's happening. So the main questions, scientific questions that motivate Solar Probe, technically there's three. I'm going to add back the fourth one that was removed during the mission formulation process because we can actually do that science, and I'll talk a bit about it. But the first one is what heats and accelerates the solar wind. So this is from a Kivelson and Russell book, but it's showing what's known as the Parker solution. So the spacecraft is named after Eugene Parker, who in the late 1950s came up with a solution for a non-hydrostatic solar wind, a non-hydrostatic atmosphere of the sun. Prior to that, the concept was that the sun must have or is likely to have a hydrostatic atmosphere, kind of like planets do, where you have a balance between gravity and thermal forces. But Parker's calculations essentially showed that you need an accelerating wind in order to not cause a sort of catastrophe at the edge of the solar system with the boundary conditions. And this is the solution he more or less came up with. And he said that the solar wind must go supersonic and it must go super alphanic. So at some point, it has to be accelerated to a point where it's propagating faster than the speed of sound and propagating faster than the ability for magnetic information to be transferred through a plasma. But what does that, right? Parker's solution just says it should in order to meet boundary conditions, but it doesn't actually say why or what the mechanism is that's driving everything. The second question is about heating, and the issue with heating is that this is, if you look at temperature as a function of distance from the sun, these are measurements from the 1970s from the Helios mission, and what they saw is essentially in the black, that's the data. The blue is an adiabatic prediction. If you took the gas from the sun and released it as a solar wind and let it expand, it is expected to cool adiabatically, meaning you're not adding or subtracting heat from the system. But it's hotter than that. Something is heating the wind as it travels outward. But the wind is not magnetically connected back to the sun because it's super alphanic, so no information can be transferred via magnetic field between the sun and the wind once it's been accelerated. So where's the heat coming from? It must be intrinsic to the wind itself. But what's the mechanism? There's also questions about what are the sources that are the structures on the sun that are the sources of the solar wind. We know there's fast wind, slow wind, transient wind, things like coronal mass ejections. So what are the source regions? That's another question you can only answer by getting very close. The third question is how are solar energetic particles accelerated? So the sun, this is an image from the SOHO mission. These are nested images from 3 different cameras that are looking at the sun. Obviously, one of them is a coronagraph. You can see the stick that's blocking out the sun. And what you're seeing there is a coronal mass ejection, what's known as a halo CME, meaning it's coming toward you as the observer. That's why it looks like it goes all the way around. And then that white fuzz you're seeing afterward are energetic particles striking the sensor and saturating pixels on the sensor. So you're getting hit by a bunch of energetic particles being accelerated from a structure at the sun. So what are the mechanisms that do that? And then finally, this one was removed late in the mission, but it turns out we can do the science anyway. So I'm putting it back here. And that's how does the sun process its dust cloud? And this is relevant to, for example, planetary formation. So say you have a pre-planetary nebula, you just have a bunch of dust around a star, the star ignites. What then does it do to that dust cloud? Well, we can look at our own star and try to understand what happens in that environment and then extrapolate to those others. Solar probe looks like this. The main spacecraft bus is back here. The heat shield is on the front. We get very close to the sun, so the heat shield must face the sun at all times. I think we get about 30 seconds of sunlight before the search coil melts off the back, which is a fun thing. The main parts that I'll be talking about today are the electric field instruments. So that's these 4 antennas that sprout out. There's another one over here in the plane of the heat shield. The search coil, which is a high-frequency magnetometer, measures magnetic fields. And these are the low-frequency magnetometers, the flux gates. There's also particle instruments. One of them stares right at the sun. That's the Faraday cup. And then there's electrostatic analyzers that live on the back. There's also the high-gain antenna, of course, to talk back to Earth, and then the solar panels. The solar panels flap backward away from the sun direction when you get close to the sun, and the whole spacecraft is powered just by that amount of solar panel. This spacecraft is only a couple of meters across, so it would fit in the front of this room very easily. It launched in 2018. Solar Probe Plus is plus because it has lots of encounters with the sun. And what it does is use gravity assists with Venus, to lose angular momentum and allow it to step closer and closer to the sun. So over the course of the mission, it's progressively been getting closer. That's why the closest approaches didn't happen until Encounter 22, which was last year, Christmas time, because they had to use multiple 7 encounters with Venus to step into the sun. CU contributed some of the spaceflight hardware. We built this thing, the Digital Fields Board. So it's a piece of the signal processing electronics that go on the field's instrument suite. The field's instrument suite rolls up into the sort of mission management and spacecraft development that was done at APL, which then, of course, rolls up all the way to NASA. So with our small section of that, what are we doing? With CU, we are exploring what heats and accelerates the wind. We're going after structures at the sources of the wind, and we're focusing on the dust cloud, and we even did some science of opportunity with those Venus encounters. Okay, so because we're part of the field's instrument, and because this is the physics that interests me, we mostly go after wave-particle interactions. So what does that mean in a broader context? A wave, for example, is a collective motion of some kind of fluid, often a periodic type motion that can transmit energy across that fluid. This is an example over the Flatirons, right? If you ever see these kind of clouds, there's your Kelvin-Helmholtz instability. So you have a velocity shear, essentially, and the clouds are kind of showing that for you or giving you kind of a tracer of that. But that's a wave that's taking place in the atmosphere. This is a simulation of the Earth's magnetosphere. And you recognize those curl-ups on the edge? That's Kelvin-Helmholtz instability. So the same math that describes what happens over the Flatirons describes what's happening at the edges of the Earth's magnetosphere, which is pretty wild. So waves and plasma facilitate energy exchange between the particles and the fields, the electromagnetic fields. And why I really like them is because they trace these plasma instabilities. So whenever you get processes that sort of add energy to the plasma or rearrange it, you get a wave. And so that can be acceleration, that can be heating, things like that. So they have really powerful diagnostic capabilities. You can use the frequencies and amplitudes and the structuring of the waves to learn things about the instabilities. And this is maybe more important, is that you can measure waves much faster than you can measure particles. So even if something is invisible to your particle instrument, a wave will be there, and you can see it and know that there was energy exchange. This is the crew of folks at CU who have been working on Parker Solar Probe. And it's a broad group. There's grad students and undergrads, postdocs, there's professional researchers and faculty, and a lot of collaborating institutions. This has been a big effort. You're going to see a lot of plots like this, so I want to walk you through one. What we're looking at here is one encounter of solar probe with the sun. So this is plus or minus 5 days from one of those close approaches. At the top, so these plots are what's known as spectrograms. So you're looking at frequency on this axis, you're looking at time on the x-axis, and then the color that's popping out at you is power. So where you see it go red, that tells you there's a lot of electric field power at that frequency at that time. So this is kind of a primary tool that we use to identify plasma waves and determine their properties. In this particular one, what you're also looking at down the bottom is the magnetic field. The black is giving you the magnitude of the magnetic field. I've mirrored it top and bottom just to make it easier to see. And then the blue is giving you the radial component, so the piece facing toward the sun or away from the sun. In this case, you can see all these structures switch halfway through. That's because we've crossed the heliospheric current sheet, or the boundary between the sort of positive and negative magnetic polarities on the sun, how that mapped out into the solar wind. This frequency that we're looking at in white, it's a little redundant because the frequencies overlap a bit. That's the electron cyclotron frequency. That's the frequency at which electrons orbit a magnetic field. So it gives you some physical reference for that wave power. So solar probe went into a new environment. No spacecraft had been here before. We'd never measured these plasma waves in situ. So some of the basic questions are, what waves are even there? What do we expect? What do we see? What are their wave characteristics? And how can we use them to understand these solar processes? So I have for you here 3 spectrograms with sound. So that's the middle one here. I don't know why it played that. I'm going to do this real quick. Here's the top one. And then the bottom one. So these are 3 different wave modes that we encounter. Well, one of them is not a wave technically, but we'll go through it. And I'm going to talk about each one of them. Nope, stop it. There we go. Good. OK. So the first one is that first one you listened to that had those little whipping kind of tones. Those are rising tone plasma waves, meaning the tone rises over time, so you hear that as a foop, foop, foop. But what these are, it turns out, are dispersive ion acoustic waves. This is something we did not expect to find in the solar wind. They look like this in a spectrogram. So again, frequency, time, power, and you see all these little vertical slice features. When we zoom in on those features, and look, this is over 10 minutes or something. When we zoom in to a few seconds, you get a lot of detail, and you can see that each one of those is a little plasma wave that's sweeping up in frequency with time. We see these on every single orbit of the spacecraft. They have a preferential radial distance, maybe, and we're pretty sure they're ion acoustic waves. So that's where my slinky wave comes in here. An ion acoustic wave is an acoustic wave, like a sound wave. It's compressing, and it has compressions and rarefactions that then propagate as a wave. But we're watching this in a plasma carried by the ions. One of the things we were able to do with these ion acoustic waves is identify them in an automated fashion. So we could get thousands of these things. And by getting thousands of them, we could look at the frequency of the wave compared to the ion plasma frequency, which is sort of the frequency you expect an ion acoustic wave. And we could look at that as a function of the angle between the magnetic field and the solar wind direction. And because we know that these waves are Doppler shifted, we can write out an expression like this. Our observed frequency that we're getting in the spacecraft frame is whatever's happening in the plasma frame, plus the Doppler shift term, which has an angle, solar wind speed, and the wave number. Well, we have most of this stuff. We know the plasma density, so we can figure out what it should be in the plasma frame. We have an observed frequency from our data. We know the solar wind speed from a measurement, and we have the angle between the magnetic field and the solar wind speed, so we can use all that to back out the wave number. And that's exactly what we did with a whole bunch of these. We came up with a wave number, which we can then use to determine a wave length. OK, that's great. Why would I want to do that? I want to do that because I can use that wave number to figure out the resonant energy. What particles are interacting with this wave? And so we went through that whole process, and what we figured out was that the resonant energy was somewhere close to the thermal velocity, maybe just right at or a little bit past. This is a bit unusual because some of the mechanisms that can drive ion acoustic waves are, for example, this kind of beam core instability, meaning that you have a core distribution of protons, and then you have a sort of secondary distribution of protons that's at a little bit higher velocity, so the velocity shifted over. And then at this point in between the two, you have free energy to exchange between the particles and the waves to grow the waves. So this is particularly interesting that we got such a low resonant velocity really close to the thermal speed. That means your main distribution and your extra distribution that's allowing the waves to grow are right on top of each other, or very close to each other. And that means the part that's being accelerated up to those higher velocities must be very dense. It must be almost the density of the solar wind itself. So we're accelerating a chunk of the solar wind, or something, some substantial piece of it, to a higher velocity than the thermal speed, and we can pick that up using these ion acoustic waves. Also, we only see them in some locations, so perhaps this is local acceleration. One of the things we're looking for is what accelerates the solar wind. Does it all happen down at the corona, or does it happen as the wind propagates out? And suddenly we have evidence that there's some local acceleration process happening. We also went one step further and went to look at the proton data. This is, again, another distribution function. It's showing you the number of protons as a function of velocity. And it's showing you for two conditions. One condition is the black solid line, which is when there's no waves present. That's this curved under here. And then this one is showing you, the dashed one is showing you when there are waves present. And what we're getting is this lump, or extra particles, at those higher velocities. Now, the particle instrument is not fast enough to resolve that extra little beam structure we were hoping to see. But what it can do is it can see this sort of plateau or remnant acceleration of the wind. So what we see often is when we go to find these ion acoustic waves, we find that accelerated distribution along with it. So then the natural question is, what is actually accelerating the proton beams that are creating these waves? We don't have an answer yet, but there are strong implications. One of the strong implications is that this localized acceleration may be related to what's known as the ambipolar electric field. So one of the big results in Solar Probe, which we did not do it here at CU, but which we're piggybacking off of, is this observation of electron distributions where some of the electrons are running away from the sun, and then going back toward the sun, the electrons are, what do they call it, in a deficit. Basically, some electrons can't make it back to the sun. And the explanation that's being presented for this is the idea that in the corona, everything is roughly the same temperature, the ions and the electrons, when the plasma is collisional. And as soon as the plasma becomes non-collisional, you have sort of the same amount of energy, but you have lighter particles and heavier particles. So the electrons, which are lighter, part of their distribution has velocities that can escape solar gravity. The protons maybe not so much, but the electrons, yes. And so when those electrons end up escaping from the sun, you have a bunch of protons back here, and now you build up an electric field. You've separated charges. And once you've separated charges, you have this large-scale electric field that, in theory, can sort of pull the protons off with it. That's one way to explain an ambipolar field. The problem is plasmas don't like doing this. If you put an electric field in a plasma, the particles will always rearrange themselves to short that field out, especially DC fields over large distances. So how does this ambipolar thing make any sense? Well, they went and looked at the electron distributions and saw electron distributions consistent with the presence of this kind of large-scale electric field, and they can even measure it as a function of radial distance and show that it accounts for something like 80% of the solar wind acceleration. But we also know there's no large-scale electric fields because plasmas don't allow that. So what can you do? Maybe that acceleration process, instead of being one giant monolithic electric field, is kind of filamented onto these scale sizes where particles can separate, which are going to be sort of Debye scales or kinetic scales. And maybe what we're watching with these ion acoustic waves is little bursts of solar wind acceleration that are then adding up to this larger scale picture that they see with the particle data. That's one interpretation that's not been proven. With those ion acoustic waves, we were able to go further. This is some work that Lily and Bob did, looking at proton beam simulations. So what if we released a whole bunch of protons from one particular location? So that's this little bump on here, right? Those are the extra protons being released. And we let that propagate through space and then try to observe it with a sort of pseudo-solar probe. What can end up coming out of that from the simulation is that you can get, again, frequency and time, these dispersive features. So these dispersive features, which we did not really expect to see as part of ion acoustic waves, you don't often see that thing when you see ion acoustic waves in other environments, can be explained by treating this as an abrupt localized acceleration. So if a whole bunch of protons are released from one location and propagate out, you'll end up with this kind of bursty behavior, which is almost exactly what we see in the data. We're also pursuing other ways to try to understand where these waves come from. There's a paper here that Sergio and Stefan worked on, which is trying to examine magnetic reconnection. We can identify sites of magnetic reconnection in the solar wind where you get jets of plasma that come out. Are those jets what we're thinking of as these localized acceleration? Turns out probably not. Actually, Sergio's work ruled that out. But he did find a strong relationship with solar wind current sheets, which are magnetic deflections, so where the magnetic field bends in the solar wind very abruptly. For some reason, this is sort of the probability of observing the plasma waves. This is a distance from, well, in time from current sheets. And where those two, when you get close to a current sheet, your probability of seeing one of these ion acoustic waves goes way up. So we're not exactly sure why that's there yet, but we know there's a strong correlation. Several undergrads have also been exploring the idea that these are driven by steepened Alfvén waves. So just like an ocean wave can break, a magnetic wave can kind of do the same thing if it has a dispersive character to it, and that may lead to some particle acceleration. Let's see, I had the sound for this one. This is the really weird sounding one. We did a press release with these sounds, and people thought that was a Halloween sounding thing, so maybe this is appropriate. I don't know. But what these are, turns out, are electron Bernstein waves. I'll explain what that means in a minute. But these are waves that really have not been observed outside the magnetosphere very frequently, but we see them on Solar Probe all the time, especially as we get closer to the sun. But it turns out they appear during very unique set of solar wind conditions, and I have an example here. So what you can see is at the top, there are the waves. This is the magnetic field, and you can see it bouncing around like it normally does in the solar wind, and then something happens, and it gets very, very quiet, right? And when that field gets very quiet, that's where the waves appear. You can also see it in the density. So the density is bouncing around happily, and then just boop, and goes flat. And then the temperature also goes flat. And this is the solar wind speed, so you can see that bouncing around, and then suddenly it pegs to a value and stays there. So there are a set of very unique solar wind conditions where these waves occur. Oh, nope, don't do that. Okay, so when we can use our high-resolution burst data captures to look at these waves, we can start to see that they're organized by the cyclotron harmonics. But they're not at the cyclotron harmonics, they're between them. And this is a feature of electron Bernstein waves. This is actually a problem you do in the graduate plasmas course, is write out the dispersion relation and the frequencies of the Bernstein waves. Well, I actually used it. So how about that? And what we also see are these other waves, which we still actually haven't identified the exact type of yet. So I just call them B and C because I don't really know what they are. But what we did see with these kind of waves down here at these frequencies is that they follow the angle between the magnetic field and the solar wind speed. And using that, and again, using the same Doppler shift trick, we can figure out what velocity particle they're resonant with. And this is where things got really weird. We found that they were resonant with the core of the distribution, the coldest particles. That doesn't make much sense. There are very few instabilities that operate on the coldest particles. That's the part of the distribution that's the most stable and really shouldn't be jumping around and changing energy between the waves and the plasma. So for a while they were wondering if this made any sense or if we made some kind of mistake. But it turns out the solar wind conditions where these waves occur are extremely specific. They end up appearing when the magnetic field is between 15 and 30 degrees away from the sun direction. But they don't follow the Parker spiral. They don't really follow the solar wind flow. So what's so special about that direction? What's so special about that direction is that the spacecraft is in the way. There's a feature called the ion wake. Just like a boat moves through water and creates a wake behind it, you get a very similar thing with a spacecraft and a plasma. As long as the flow velocity of the ions or electrons, in this case the ions, is greater than the thermal velocity, then they can't fill in behind the spacecraft. They kind of move ballistically past it. So what you get back here is a deficit of protons. The electrons, on the other hand, are much hotter and they can fill in. So you get a charged structure behind the spacecraft. So what we end up seeing is that when the magnetic field aligns with the wake, these waves show up. But not all the time. The ion wake is always there, but the waves aren't. So we're missing some ingredient. Turns out what we're missing is a thing called the electron shadow. Again, the spacecraft. So if we start looking at the energies that I calculated before for the resonant energy, we find something like 0.1 eV. If I get the gyro radius of a 0.1 eV particle, so how big of a circle does it make about the magnetic field, I get something like 3 meters. Well, you know what else is 3 meters? Is the spacecraft. So the spacecraft, whenever the magnetic field threads the spacecraft, it's absorbing these low energy electrons. They cannot propagate through the spacecraft. So you get basically a shadow wherever the spacecraft is that kind of blocks some of those particles. Now, when those two things align, when the ion wake and the electron shadow align, you get a distribution function that looks like this. So what you're seeing here, well, let me go to a different one first. This is your normal case. What you're seeing here are the electrons. So this is the number of particles versus the speed. And then you're seeing the protons. The protons are a much narrower distribution because they're heavier, right? So for the same amount of energy, they don't hit as high of a velocity. So you get this tight-looking thing. The electrons spread out. This is the normal condition when you have no wake and you have no shadow. If you go into the shadow, you cut out the cold electrons. But the protons are still there. If you go into this condition of the ion wake, you have the protons are missing because they can't make it into the wake, but the cold electrons are still there. If you line the two up, you get this kind of gap in the middle. And that gap is a positive slope in the distribution function, meaning you can exchange energy between the particles and the waves. So suddenly that thing that didn't look physical at all, those very cold particles driving those waves, turns out to be something that actually can drive waves under the condition that you remove the protons also. But we're only doing that because of the spacecraft. And when we go and look at this to verify it, now I'm looking at the amplitude of the waves as a function of the angle between the magnetic field and the wake direction. Look at that. Every one of these waves pops out to high amplitude once the two align. So on the one hand, this was kind of disappointing because it wasn't solar wind physics in the end. It was just our spacecraft disturbing the environment. But on the other hand, we learned a lot from it, as I'll tell you in just a second. So the third science question that we went after is interplanetary dust. The solar system is full of dust. These are the leftovers, the remnants from planetary formation, also bits of comet and asteroid. As these things get close to the sun, the electromagnetic forces that can push them along get the strongest because you're getting to the highest magnetic fields. The radiation pressure that can push them along or destroy them gets strongest. The density gets strongest. So dust slowly marches in toward the sun through a process called Poynting-Robertson drag. And then the destruction of dust particles by sublimation or sputtering also gets strongest as you move in toward the sun. So all the dynamics that affect our dust cloud should get more and more intense as we get into the star. And how do we even measure this with Solar Probe? It has no dust detector. Well, it has an electric field instrument, and therefore it has a dust detector. What ends up happening is that dust grains, which are very small, we're talking micron or submicron particles, so things that you can't even really feel between your fingers as a grain of sand, smaller than that, when they hit the spacecraft, they explode. They're hitting with so much kinetic energy, you get an explosion, so they vaporize, and then that vapor immediately ionizes, and you get a plasma cloud about the spacecraft, or a plasma explosion. And once you do that, now you have charged particles, and now you're disturbing the potential near the spacecraft, and we can pick that up as a spike in the electric field instrument. So that third sound you were listening to, that hiss, that kind of sounded almost like rain, that's the dust impacts over the course of one perihelion encounter. We get hit with thousands and thousands and thousands of these. The spacecraft is being sandblasted, literally, because it's probably silicon, a lot of it, or silicates anyway. So these dust impacts make these clouds. We can measure these as voltage spikes, and your whole spacecraft becomes your detector. So even though they threw off our very small detector where we wanted to measure the properties of the dust, we still have the whole spacecraft by which we can count the impacts. Oh, yeah, there's the sound. So each one of those pops you hear is another impact over the course of a couple of days. So what have we done with all that information? One of the things we did was create a dust impact database so other people can use this for studies of asteroids and comets and solar processing of dust. We made this into a publicly available data product that everybody can use now. We also found, and this was work led by an undergraduate, Anna, she determined that there is a novel dust destruction mechanism, something that had not been taken into account when we're trying to understand the balance between sources and losses of these small grains in the solar system. So what she was doing was using the fact that these antennas, we have 4 of them in the plane of the heat shield, and so when an impact comes in and strikes the spacecraft near one antenna, it makes a larger signal on that antenna than on the others. So we have a crude direction finder. Now we have kind of a 90-degree on the sky kind of idea where the dust is coming from. And so during the course of an orbit, as the spacecraft was coming around the sun, right about here, the spacecraft started getting hit in the back, the direction where we did not expect dust to be coming from. And so that was, again, some work that Anna put together. And the explanation for this, Jamie Soleil at Princeton put together this idea that it turns out where the spacecraft was getting hit from behind is related to the Geminid meteor stream, or the debris stream that come behind the particles that create the Geminid meteor shower. When that meteor stream interacts with the already dense zodiacal cloud near the sun, there's extra collisions. So the collision rate goes up, and it produces a spray of very small particles that come out at an angle just right to produce that anomalous detection on Solar Probe. So the idea here is that any comet or asteroid stream that approaches and passes through the inner solar system enhances the grinding rate of the zodiacal cloud. And when you take that into account, you can make new estimates of how efficiently the star is destroying the zodiacal material or ejecting it from the system. So that's what we ended up doing with that study. It got some press attention, so we got a really cool video out of it, which was kind of fun. And this kind of illustrates the thing that I just described. So normally, very small particles can be pushed out by solar radiation pressure, forming a thing called a beta meteor. That's what's being shown here. And then what they end up showing in just a second, come on. OK, I promise it's coming. There we go. That's the orbit of the debris that make up the gem-emitted meteor stream. And when that debris interacts with the dense part of the zodiacal cloud, it creates this extra stream of betas. And that allowed us to estimate the erosion rate of the zodiacal cloud. Also, we found this thing on Solar Probe where we see debris clouds. And I don't mean just the plasma debris, but pieces of the spacecraft come off at some of these impacts. We're hit with such high energy impacts that it takes off some of the paint, some of the MLI, multi-layer insulation that keeps the spacecraft at the right temperature, and other pieces fly off. So what you're observing here is a white light camera on Solar Probe that's looking sort of 90 degrees to the sun. This is right before an impact, this is during the impact, and this is after the impact. And during that time, what we saw on the electric field instrument is this huge spike that lasted, potential perturbation that lasted for almost a minute or more, which is crazy because usually you expect these things to be microseconds. And here we have one lasting for a minute. So what happened, or our interpretation, is that when it hit the spacecraft, it created a cloud of chaff that's traveling with the spacecraft. And once that material then charged up, the solar wind picked it up and pulled it away from the spacecraft. But it took some time to do that because the particles were kind of large. So we create these charged debris clouds, and we can watch the plasma waves created by the pickup process. So when people look at planetary atmospheres being lost, for example, through pickup processes, we have an experiment here where we know the source, we know what the material is, and we can watch the pickup process happen. And so we can understand some details about the pickup physics that we can then extrapolate to these other environments. And then a recent study was looking at near-sun meteor streams, again using the directionality data. I'm not going to get into that one, just to say that we identified the idea that this near-sun thermal stresses, that things we don't think of as bright objects, not a comet, but just a rock, basically. When it gets close to the sun, the thermal stresses on the surface can still eject material, even if it's not enough to make something that looks like a comet. So using, switching gears just a little bit, these plasma waves and these special solar wind times turned out not to be related. Oops. It just happened that the magnetic field was aligned in the right way to create these wake waves. But when we go look into these quiet solar wind times in general, it turns out they have very special properties. They have magnetic fields that basically align with the Parker spiral, which was a prediction that Parker made for the structure of the solar wind. Their magnetic field becomes extremely stable, and they behave almost exactly like Parker's analytic solution from the 1950s. So all the extra turbulence and acceleration and all the things we normally see in the solar wind, they go away for these slight intervals of solar wind that we found using the waves by accident. So graduate student Ben Short has been looking into this for his thesis. And what he's doing is tracking the properties of what we're calling these quiescent regions. And he's finding that they have very peculiar properties in terms of the solar wind speed, the magnetic field structure. They're very stable. They're not prone to plasma instabilities at all. And for these reasons, we think they are pristine solar wind, unaffected by other acceleration processes. So they're probably the base form of the solar wind, and everything else that happens is some other effect on top of that. And this is some work, so I'm not going to explain this plot so much, but Ben has been trying to map these things from Solar Probe magnetically back to the solar surface and trying to see if they line up with supergranule boundaries or not, which was one of the theories for where they come from. Turns out we can't actually tell. And then finally, Solar Probe has flown by Venus 7 times. And as it does that, we get some unique data. This is actually an image taken in white light by the Solar Probe Whisper camera as it went by Venus. And this, see all this stuff? Those are streaks of material from a dust impact that are flying in front of the camera. Kind of fun. But one of the things we were able to do at Venus was weigh in on the lightning debate. So there's a sort of 40-odd-year-old debate on whether or not there's lightning on Venus. And one of the strongest pieces of evidence for lightning on Venus came from the Pioneer Venus Orbiter spacecraft that was active through the 80s and 90s. And the idea here was that we see what's known as a Whistler wave. It's a type of plasma wave. And at Earth, we know that Whistler waves are triggered by lightning strikes. And so if we see a whole bunch of Whistlers near Venus, which is what was seen with PVO, they said, yes, there must be lightning. Much later, this Japanese spacecraft was there looking for optical flashes of those lightning strikes. They looked for, I think, 3-4 years, and they saw absolutely nothing, not a single optical flash that they could definitively call a lightning strike. So, okay, yes, there's lightning. No, there's not lightning. With Solar Probe, we can weigh in. With Solar Probe, we have both electric and magnetic fields, and so we can get the pointing vector. We can see which way the waves are propagating. And what we were able to show is that, yes, there are Whistler waves. They're propagating toward the planet, not away from the planet. Not only that, but we have a much broader frequency coverage than prior missions, and we can see at the same time these waves called Langmuir waves, which are often driven by electron beams. And so now we can interpret these Whistler waves as being driven by beams of electrons accelerated elsewhere in the Venus system that are going toward the planet. So we kind of come in on the side of the Atsuki spacecraft. Oh yeah, and then this awesome, got this really cool title. We got on Science Friday with this, which was a lot of fun. I listened to that show as a kid, so I was super excited to be on it. And they came up with a great title. Okay, so that's the there. Let's do the back again in 5 minutes or less. We learned a lot of fundamental physics through the Parker Solar Probe mission, but it's enabling exploration here. So those wake-driven plasma waves that we thought were just really annoying things on Solar Probe, it turns out we can apply that to the near-Earth plasma environment. Everything makes a wake in a plasma, including spacecraft and debris. And if we can measure the electromagnetic wake coming off another spacecraft or a debris, that gives us a way to detect things that are otherwise not detectable from the ground. So we're exploring this with a current grant as a way to identify space debris. Those dust impact clouds that we found, it turns out the physics that we learned from those kind of clouds we can now apply to create this detector. This is what's known as the dense detector, and this is for detecting debris in low Earth orbit. So we're using that same physics as a detection methodology instead of something accidental on Parker Solar Probe. That hardware that we built up for Solar Probe, the flight spares have now been incorporated into a lunar lander as part of the NASA CLIPS program. This will be going to the lunar surface to measure the surface electric field as the moon interacts with the solar wind. Those algorithms that we developed to process the data on board, those are now powering instruments on sounding rockets that are exploring the interaction between Earth's neutral and plasma ionosphere and atmosphere. And then those algorithms have also been developed or parlayed into this Canvas CubeSat, which is looking at lightning whistlers, which is kind of a fun connection back to Venus. But here we're looking at them at Earth on a CubeSat. And then finally, both of those things together have been proposed for the Artemis 4 human mission, crewed mission to the moon, to deploy an instrument onto the surface measuring both the dust and the electrostatic environment and how the two interact. That's currently a pending proposal. So that's the there and back again. These things we learned about Bernstein waves, the actual hardware, what we learned about dust physics has enabled exploration of the lunar south pole, the ionosphere, the lunar surface with humans, again, lightning-driven plasma waves, and even the LEO debris environment. And finally, Parker Solar Probe will be going to the Smithsonian. So this is the model that will be, it's actually part flight spare, part model, that will be in the Air and Space Museum soon. And these are two CU undergrads, obviously very excited to be there, seeing this thing at AGU last year. And finally, we're headed into extended mission, where there's also DKIST and Solar Orbiter that are active. And this is the last slide, but given the time, I think I'll just I'll read it. Because what we wanted to know is what heats and accelerates the solar wind. So we looked at ion acoustic waves, and we're treating them as tracers of this cold, dense proton acceleration. We looked at quiescent regions. These give us a novel test of acceleration theories because they show us kind of the baseline operation of the solar wind. What solar structures are at the source of the solar wind? We've been trying to trace the quiescent regions back to those solar structures. How does a star process its dust cloud? We can go after this question by examining those impacts on the spacecraft. And we got some extra physics of opportunity out of this thing by looking at the Bernstein waves, which give you interaction between a spacecraft and its environment, as well as using the Venus encounters to really, maybe not solve, that might be a little strong, to weigh in on this 40-year-old mystery of lightning at Venus. And going forward, we have this array of new missions and measurements that are all made possible by these scientific studies and the hardware developed as part of them. And Solar Probe itself, of course, will continue on into the extended mission. So yeah, thank you. Much appreciated.
Okay, thanks, David. We'll go to questions in just a second, and hopefully student questions first. Just 2 comments quickly. First of all, David demonstrated a scientist's humility when he corrected the word solved to weighed in on. Scientists are always scared to, not scared, but apprehensive about saying it's done. Nice. And then the other thing is, at the end, I thought it was a really great demonstration of how asking one science question leads to new projects, new environments, the next thing all the time. And for me, is a great demonstration of why it's important to fund basic science. With that, are there any questions? Okay, let's go Juliana and then back here.
Hi, great talk. So in the beginning, you said that this is the closest that Parker's ever going to get to the sun. Is that because of the orbit? Because you said it's going to extend. Is there a reason it can't go any closer? Or?
Yeah, there's a couple of reasons. One, the heat shield is not rated for any higher temperatures, so they technically could move it forward, but the heat shield would be likely to fail. Second, the Venus encounters are not going to happen for a while. The next Venus encounter is in 2032, so the orbit pretty much has to stay where it is because there's no planet to push off of anymore. And there's not enough fuel on board to significantly change the distance. So yeah, it is where it is for a while. And actually, just one more fun thing about that, when the mission does end at some point, because it will die eventually, the most poetic thing about the mission is that it will become the solar wind. As soon as it tilts, right, it'll melt, and then it'll vaporize, and then it'll ionize, and then it'll get picked up and blow right out. Except for the heat shield, that'll be there more or less forever.
In the case of the dust impacts, where you had some of the material from the spacecraft contributing to that longer signal, did that appear on all 4 of the antennas?
Yes, but with different amplitudes. And one of the things we were actually able to do later in the mission, when we were sort of testing how much of that material stayed near the spacecraft, was we were able to heavily bias or change the voltage on one of the antennas. And what ended up happening was those debris particles ended up orbiting the antenna, and we could watch it with the camera on Solar Probe. So what we worry about, and why you might worry about this in other conditions, is that that material is charged, right? And so like glitter, right? You ever try to get glitter off your hand? So they can electrostatically stick to you. Well, that material can electrostatically stick to the spacecraft and short out spacecraft surfaces that we don't want shorted out. And as part of that, to try to blow the material off, we tried to change the potential of the spacecraft drastically and sort of poof it away. That actually worked. And when it happened, the material ended up orbiting the antennas, and we could see that. But yes, it was more on one antenna than another.
There was one here. And then we'll open it up to anybody next.
Will Parker Solar Probe ever fly by Mercury? Why or why not?
Ooh. It's not part of the mission planning, so they never planned to go close to it. I imagine they would try to avoid it, but it's a small object, and I don't know, really. I don't think anybody's ever addressed that directly. I'm not sure. I imagine the mission planners know, but I don't know.
Any other questions?
Now that Parker Solar Probe has gone through a whole period of observation, you've got these great results, learning a lot of things, moving forward. Is there a particular instrument or measurement that, in retrospect, you wish you had added to this spacecraft, or a set of measurements that extended your capabilities in some way that future people might want to think about?
Well, for one, a dust detector, right? That was supposed to be on there but was removed. But really, ion composition, I think, would be the biggest thing. So the ion composition measurements were thrown off even before the dust detector was thrown off due to mass reasons. But I think it's one of the more critical measurements because it allows you to map things back to the solar surface with much higher precision than what we're doing now. What we're doing now is more or less guessing based on some of the alphas that we can measure and then trying to use magnetic field models to map back, but they're imperfect. The composition would have been much better. We also could have addressed the inner source pickup problem if we had the composition instrument.
You mentioned the ambipolar field of the solar wind and talked about how this large-scale field might be composed of a bunch of little filamentary structures. But you said that this is a speculation. This isn't yet proved. What will it take to prove that?
So one of the things we're also doing with some of the burst data is we're looking at these very small Debye scale electric field structures that we do see in the solar wind. And if we look at enough of them, we can sort of integrate across these electric field structures and try to figure out if they carry a potential. And if we do that, and we can measure those little incremental changes in potential and basically say, what's the filling factor of these structures? Does it add up to what the particle instruments are seeing as the global field? So that's the approach, and that's a proposal that's out now.
I have a question about the ion acoustic wave generation mechanism. I was kind of curious about the distributions you showed, how even though there were the sort of warmer distributions in the case that you did detect ion acoustic waves, you didn't necessarily see any evidence, or at least a clear signature of a quasi-linear plateau or anything like that. Yeah. I mean, what kind of other mechanisms do you think about, like parametric decay, that could also generate ion acoustic waves but not necessarily rely on there being a beam population?
Yeah, the issue with parametric decay is we don't really see other wave populations present at the same time. So that's one study we did, was to try to correlate them with things like Whistler's or Langmuir waves or something else that might parametrically decay. We don't really see that. The other was sort of steepened Alfvén waves, or is there some kind of Alfvénic decay process? But again, there's nothing unique related to the correlation that we found yet, related to the correlation between the Alfvén waves and the ion acoustic waves. So we just haven't found anything like that, even though we've been looking for it. The issue here, you mentioned you see kind of a plateau, but you don't really see a peak or anything. This is integrated over 7 or 8 seconds, right? And if you're integrated over 7 or 8 seconds, where's my wave? Each one of these waves is a very small fraction of a second. So we're smoothing the heck out of that particle distribution by taking a long time interval to collect the data. So if we had something like MMS, where we could get millisecond particle distributions, then you could see something like that, or at least make that test. But as it is, we have to infer everything from the waves.
Okay, 2 more questions. We'll do Taylor and Ethan.
For your connection between the dust and the meteor orbit, does that only happen with those particular meteors, or does it happen with other orbits as well?
Yeah, sorry, I had to zip kind of past that one. The issue right now is that there's actually only one encounter that had the electric field instrument configured in such a way that we can use that directionality analysis. We're trying to come up with ways to sort of recover that information from other orbits, but we've not been successful so far. So what we did was, with that closest encounter, encounter 22, which was the one in December of last year, we changed the mode of the spacecraft. So from that encounter onward, which is the data that's coming down right now, we have the ability to do that again and look for those meteor streams. But prior, there was only one encounter configured the right way. So ask me again in 6 months.
So you talked about these quiescent regions and using them to try to connect the environment back to the solar surface, and kind of found that to be inconclusive. But I'm curious if you were able to make that mapping, what that would have taught us about the underlying connection.
Yeah, so this is the plot I didn't get to talk through, so thank you. This is the solar wind velocity. So the bulk velocity is a function of radial distance. And you can see this kind of acceleration profile that kind of plateaus. And what Ben has done here is he's marked the typical behavior, sort of, I think it's medians and quartiles, of the quiescent wind in orange and of the general wind in blue. But what he's sort of eliminated from this kind of plot is all these spikes. The solar wind has these sort of streams of much higher speed solar wind, but they're localized spatially into these tiny little spike jet things. the base behavior of the wind that follows Parker's solution is almost entirely the quiescent wind. So if we can figure out uniquely what solar structure they're coming from, we can sort of say, what is the base acceleration? You know, what is the piece of the sun that is creating the background solar wind? And then on top of that, we may have things like jets or spicules or whatever that create these extra bursts that create the vast majority of the wind. The other thing that Ben sees is that these quiescent regions, as you get closer to the sun, there's more of them. They take up a larger fraction of the solar wind. And as you move away from the sun, once you get to about 40, they're more or less gone. They're down to 1% or less of the wind because they've mixed with the background.
Okay, so now I'm reflecting on David's comment that you ultimately become the thing that you study, and I'm questioning some choices I made in the past. I think maybe I should have studied dolphins or something like that. But with that, let's thank David one last time. And David said he would stay here till 7 p.m. answering any questions that you have as well.